We're now ready to begin a brand new topic in physics, and that is the big, huge topic of electricity and magnetism. We're going to start with electricity and then move into magnetism and then see how they are connected to each other. It'll turn out that they are very connected to each other and that they are just two different aspects of the same phenomenon. This is, it'll be very hard to overestimate how important this is, and it's a huge chunk of how the universe works that we have not paid attention to at all up to this point, and it is time to fix that. So electricity is such a huge part of our lives. Electricity makes so many things that we use on a daily basis. It makes them work, right? Light. It makes light work. Phones, TVs, radios, computers, transportation, right? Light itself, so when I said light up here, I meant like electrical lights, but electricity is behind light itself, light that comes from the sun, so that without electricity there would not be sight. Radio waves, rainbows, all part of electricity and also magnetism. And even beyond that, the reason your muscles are able to move is because of electrical impulses. So electricity makes it possible for your muscles to move, for you to feel things. The sense of feel or touch is all electrically based. It's what allows your heart to beat, and it's what allows your brain to think. It's all electricity behind it. So when you see the things that are on this list, you realize how absolutely central electricity is to everything. We're going to start with electrostatics. So we'll explain what that means as we go, but that's just the basics of electricity. The static part means we won't have flowing electricity necessarily yet. So we won't be studying like electrical circuits yet, where the electricity is flowing around the circuit. This is electrostatics. Okay. So, a little bit of history. The Greek word for amber is electron, and that is actually where the root for electricity and all the related words comes from. So the word for amber is electron, because the ancient Greeks knew that if you rubbed amber with an animal fur, if you rubbed it vigorously, then the amber would be able to attract small little crumpled up bits of leaves, for example. The leaves would jump up and stick to the amber if you rubbed it. So that's really weird behavior, and what's going on there. And so amber became associated with this idea of electricity. That's just a historical kind of curiosity at this point, but that's where that word comes from. Similarly, if you take a glass rod or a plastic rod and you rub it with something like silk, you can do the same thing. You can create something which will attract small objects. And we will do this in class. I'll show this to you. Furthermore, what we find is that depending on what you rub, those two things may repel each other or attract each other. And so through some experimentation, you can kind of figure out that there's sort of two kinds of phenomena going on that are kind of opposite of each other. So what we now sort of postulate is that there is this property that all objects have called electrical charge. Electrical charge. So this is a fundamental property of objects, just like mass. So objects have mass, objects have electrical charge. And it's just this thing that things have, and as I said, there seem to be two kinds, and we call them positive and negative. So there's positive charge and negative charge. This is due to Benjamin Franklin. He's the one who kind of set in stone which kind is positive and which kind is negative. We'll find out later that he kind of got it wrong, because it wasn't his fault, but he didn't realize the underlying phenomenon that was going on at the atomic level. We weren't aware of that back in the 1700s, and things would be slightly easier if he had switched them. If what he called positive, we called negative, and vice versa. I'll explain that in just a couple of minutes. But yeah, it would be nice if it were the other way around. But in the end, it doesn't really matter. You can give any names you want to the two kinds of electrical charge. And objects of the same type of charge experience a mutual repulsive force when near each other, and objects with opposite type of charge experience an attractive force. So if you rub two pieces of amber and then put them near each other, there'll be a very slight repelling force because they're both amber and they'll both have the same kind of electrical charge. But if you rub if you rub two glass rods, similarly, they will repel each other. But the amber and the glass rod will attract each other because they are opposite kinds. They're one's positive and one's negative. I think in that case, the glass rod, a vigorously rubbed glass rod, is positive, and the amber is negative. I think that's the way it goes, but I always get that mixed up. Now, a lot of things don't have any charge, or we would say they have zero charge, and we say that they are electrically neutral. So it's just semantics whether we say all objects have charge and neutral or zero is one of the possibilities, or if we just say some objects have charge and some don't. However you want to think about it. I kind of think of everything has a charge, and it's just one option is it's zero charge. Okay, so it turns out we can quantify charge, and the units we use are coulombs. Okay, and this is a fundamental unit. This is not in terms of mass or length or time. So this is considered its own fundamental unit. It's its own dimension, I should say. And it is a signed quantity, S-I-G-N-E-D, quantity. So it can be a positive number or a negative number. And you can add. So if you take something with 2 coulombs of charge and something with -5 coulombs of charge and put them together, that system of the two things together will have -3 coulombs of charge. And that all bears out in experiments. We have a law called the conservation of electrical charge, and it says that in an isolated system where charge can't come in or leave, the total net charge is conserved. It must stay the same. Okay, so that's an important law that we will use. Okay, now, so charge is a fundamental property of the things in the universe, but we do have a little bit more we can say when we get down to the atomic level. So here's an explanation of what's going on at the atomic level, and it is certainly, I bet, something that most of you are aware of, which is that atoms are made up of electrons, protons, and neutrons, and it's the electrons that are the things that have the negative charge. It's the protons that have the positive charge, and the neutrons are neutral. They have no charge. So that's what's going on inside an atom. And an object overall can have a positive charge if there are more protons than electrons. And vice versa, you can have a negative charge if it's the other way around, more electrons than protons. And how that comes to be, how you can have more of one than the other, usually is because of the electrons. The electrons either get added in or they get stripped away. The electrons, they're a lot smaller than the protons and nucleus. They are not in the nucleus of the atom. They orbit around it, and they're the ones that you can either gain or lose in most cases. So it's the electrons that are getting moved around, and that will cause you to have either a net positive charge or a net negative charge. An ion is the name of an atom that has either gained or lost an electron, so they don't have the same number. The typical case for an atom is to have the same number, but if it's gained or lost an electron, that's called an ion. So yeah, so as I said, objects typically have charge because they have lost or gained electrons. Now, this is where Benjamin Franklin, it would have been nice if he had switched what he called positive and what he called negative, because it's really the electrons that are kind of moving around. So it would have been nice if electrons were considered positive, but as we've already said, they're not. Electrons are negatively charged according to how Benjamin Franklin set things up. So I'm actually going to go back to this page and write in. So there is what's called the fundamental charge, which we denote E, and it is 1.60 times 10 to the negative 19 coulombs of charge. And a proton, that's how much charge a proton has. It has positive that much charge, whereas an electron has negative E coulombs of charge, negative 1.60 times 10 to the negative 19 coulombs. Okay, so this is kind of like, this is the size of the package that charge comes in, because typically electrons, 1 electron's worth, 2 electrons worth, etc., of charge getting moved around. Okay, you see it's a small amount, so 1 coulomb is a good bit of charge, certainly at the atomic level. Okay. A little bit of terminology that we want to talk about. Let me do this in parts. So depending on the object, we're talking about the macroscopic level now. Back at the macroscopic level, we can categorize objects. One category is insulators, electrical insulators. And that's sort of the, I would say, the status quo. That's what we think of most things, which is that the electrons are fixed in their atoms. They're stuck there. And it takes a little bit to get them off. Okay, so that's an insulator. So most things are insulators. Glass is an insulator. Stone is an insulator. Yeah. Water is an insulator. Plastic is an insulator. I should say pure water is an insulator. I should be careful here. Pure water that doesn't have any metallic minerals in it is an insulator. Once there are minerals in the water, it actually changes because of that. But pure, true H2O water is an insulator. And what it takes to either get some of those electrons off or put some electrons on is actually friction is one way you can do it. So we can charge an insulator through friction. And that's the rubbing that we were talking about earlier. If you rub amber with fur, those atoms are really interacting with each other very roughly, the fur and the amber, and some electrons will get scraped off of one atom and go to the other, just through friction. There's actually a word for this. This is called triboelectricity. And that just means charging things through just pure friction, just mechanically rubbing and the friction that's involved with that. Okay. But the next category are conductors, and this is often metals. You want to think of metals mostly for this, and also water that has metallic minerals in it. And what happens with a conductor is that the bonds between the atoms are such that there's usually one extra electron that kind of like gets left over. In other words, the two atoms kind of bond and they kind of share an electron, but maybe then one electron is left over because they're sharing. That kind of leaves space for one electron left over, and this happens all over the place. And so what happens is you have a bunch of basically free electrons that can kind of just float through, sort of. At least that's a simple way to think about it. You have these free electrons that can just move around almost at will. So that's a conductor. And so it's a lot easier to get electrons to move around in a conductor. You can also do it with some liquids that have free ions. So it doesn't have to be free electrons. It could be a whole molecule or a whole atom that is charged, that is just free to move around. And that can happen too. That would be another kind of conductor. And there is sort of a middle ground between conductors and insulators, and those are called semiconductors. And an example of that would be silicon. So it's just the electrons can move around, but not as easily. They kind of hop from one to the other, and they kind of get stuck in an atom. Then it doesn't take much to pop them out and move again. And so it's not as freely moving as the conductors, but there is some charge that can move without too much trouble in a semiconductor. And that's nice in some cases because it can be controlled easier. So that's why silicon is often used in electronics.